they are going to have, opposite charges, and those opposite charges are going to have attraction towards each other. So the energy that is given out, the energy that is released when these oppositely charged ions are coming together to make a crystal lattice, that is known as lattice energy. So when those oppositely charged ions, because it's an attractive force, since it is an attractive force, energy is going to be released as they come together. Since they want to come together, they want to be with each other. In that process, energy is going to be released. That release of energy as those opposite ions come together with each other, that energy is going to be known as your lattice energy. So you can go ahead and define lattice energy as, let me type this out for you. The enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. So when 1 mole of any ionic compound is formed from its gaseous ions under the standard conditions, what are standard conditions? We have a temperature of 298 kelvins, right? And we are going to have a pressure of 1 atmosphere. Those are the standard conditions. So under the standard conditions, when 1 mole of an ionic compound is formed from its gaseous ions, that will be lattice energy. So a simple way of writing down the equation related to that is going to be that, let's say let's go really simple. Let's go sodium chloride. So we have got sodium. So we will have sodium ion again in its gaseous form, and chlorine ion or chloride ion again in its gaseous form. So when sodium ion and chloride ion will react with each other, I will end up getting sodium chloride, which would be in a solid state. And since this is going to involve release of energy, it's going to be a exothermic reaction, and your enthalpy change is going to have a negative sign associated with it. Okay. So lattice energy is always exothermic, always, 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 always going to be exothermic. It is always going to have a negative sign associated with it because it involves bonding together of ions, not the separation of ions. The larger your exothermic value, the larger, the more negative the value for your lattice energy, the stronger the attraction between the ions, right? For example, let's talk about magnesium chloride. Since magnesium chloride is going to have a charge of 2 plus, the attraction between the positive ion and the negative ion is going to be greater. And since the attraction between the positive ion and the negative ion is greater, more energy is released. The value for enthalpy change is going to be even more negative, right? Now, it is actually really hard. In fact, it is impossible to determine this lattice energy directly from a single direct experiment. I cannot just do one experiment and that is going to give me the energy released, right? That's going to give me the value for lattice energy. I can't just go ahead and do that. I have to use a multi-step experiment. That multi-step experiment is known as the Born-Haber cycle. We use this multi-step experiment. So we will take our compounds, we will have to do several reactions, measure the enthalpy change of those several reactions, and that will allow us to calculate the lattice energy. And the particular several, it's be do certain reactions, right? Those certain reactions are then going to come together to give us the Born-Haber cycle. But before I can explain to you what Born-Haber cycle is, you need two pieces of information. One piece of information is related to your AS level. Your enthalpy changes that you studied in your AS level, you have to remember them. Enthalpy change of formation, enthalpy change of combustion, all of those terminologies you do have to remember. Another thing that you need to, other than those background information, there is additional stuff that you need to know. You need to know two additional definitions, one of which you might have already studied in your in your AS level. That is standard enthalpy change of atomization. What is standard enthalpy change of atomization? It is the enthalpy change when 1 mole of gaseous atom is formed from its element under standard conditions. What do I mean by this? Let's say I want to calculate the lattice energy for NaCl, sodium fluoride. To do that, I will first have to turn my sodium from a solid into a gas, because the standard state for sodium is solid. It's a metal. It is solid. I need to turn that solid sodium into a gaseous sodium. So the first step, or one of the first things I will have to do, doesn't have to be the very first step, but one of the first reactions I will have to do is I will have to turn my solid sodium. Sorry, one second. I will have to turn my solid sodium into gaseous sodium. So when I am going to take 1 mole of a gaseous atom, right? So I have my sodium, and that is in solid state, and it is being turned into sodium ion in gaseous state. I'm doing atomization. That is one of the first step in the Born-Haber cycle, turning it into an atom, turning it into a gaseous atom. So that would go ahead and that would allow me to proceed with the rest of the steps. That's one of the first terminologies that you need to know. Okay, remember this, that the atomization is generally an endothermic process. Okay, it's pretty much always an endothermic process, meaning that I will have to provide some heat energy to break the bonds that are holding the atom together, right? Because it's in a solid state, so it has strong forces of attraction. So I need to break the strong forces of attraction to turn it from a solid into a gas. So it's an endothermic process. I will need to provide heat energy to do this. After I have gone ahead and done atomization, there is one more definition that we need to know, and that is about electron affinity. The energy change occurring when a gaseous non-metal atom accepts 1 electron. When a gaseous non-metal electron, what do I mean by that? I have managed to get my hand on sodium. I managed to get my sodium gaseous atom. Wow. What am I going to go ahead and do when I need to, by the way, just one small correction. I have written over here a plus sign. It's an atom, it's not an ion. So there is no plus sign. There's going to be no charge on the sodium. It's going to go from solid sodium to a gaseous sodium. It's going to remain an atom. It's not going to remain an ion. That is another step. We will have to turn it into an ion. That's on you and me. We have to turn it to an ion. But atomization is when it's going from solid to gas. So there is going to be no as such charges present. Okay, it's an atom. So just a small correction. Now, I have managed to get my sodium into a gaseous state, and I can turn this into a sodium ion. Fine. What about my chlorine? I have chlorine. I don't have to worry about atomization of chlorine because chlorine is already present as a gaseous atom. But I need to make it turn into a chlorine ion. For that, I will take a look at electron affinity because I'm taking a gaseous non-metal and I'm making it accept an electron so it can turn into a negative ion. This is electron affinity, right? And the way you define it is going to be like this. So when you talk about electron affinity can be first, second, third. Just like we had first ionization energy, second ionization energy, third ionization energy. That was what we had studied in our AS level, right? So just like that, if I'm adding first electron, the very first electron, it's the first electron affinity. Then I add another electron, so that is second electron affinity. For example, I have oxygen. So I take my oxygen in a gaseous state and I want to give it a charge of 2 minus. So I will first add an electron and give it a charge of -1. This is the first electron affinity, the need energy I need to give, or the enthalpy change that is occurring. Not the energy I need to give, basically the enthalpy change that is occurring for me to take it to from a atom into a -1 ion to add that one electron. That is going to be your first electron affinity. Then if I take that -1 oxygen and I go ahead and I add another electron to it and I make it oxygen 2 minus in gaseous state, that is going to be the second electron affinity. Okay, so the electron affinity just like that. So it can be first, second, third as well. If you talk, for example, about nitrogen, it can have a charge of -3, so it can have a third electron affinity as well. And how exactly am I going to be defining electron affinity? So the way you define, let's start, let's say, with the first electron affinity, right? So first electron affinity is the enthalpy change. When 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous -1 ions under standard conditions. Similarly, if anybody asks you to define the second electron affinity, the concept is exactly the same. The second electron affinity is going to be the exact same definition as this. Only we can change this to second electron affinity. And the charge is going to go from 1 mole of electrons is added to 1 mole of gaseous -1 ions to form 1 mole of gaseous -2 ions. Similarly, if they ask you to define third electron affinity, you will say that the 1 mole of electrons is added to 1 mole of gaseous -2 ions to make them into -3 ions, right? So these are the definitions that you need to know, or the concepts that you need to know to actually go over the Born-Haber cycle. Is there any question that you have so far on the topic?
No, but beside that, I want to ask, is there a term for metal as well when we're turning it
Ionization,
into an ion?
ionization. That's ionization. So when I take an
Okay.
ion and I make it, yeah, that's not specifically just for metal. You can apply that to a non-metal as well. But as long as you're turning it into a positive ion, because metals generally we don't turn them into negative ions, metals are going towards positive. So when
Right.
I am removing electrons, that is going to be ionization energy. And when I'm
Okay.
adding electrons, so we generally add electrons to non-metals. So that is going to be your electron. So electron affinity is the opposite of ionization. If you're adding electrons, if you're removing electrons, we are ionizing it. If you're adding electrons, we are going towards electron.
Okay, got it.
Got it? Okay. So the first electron affinity, the first value is generally negative, right? The first electron negativity, it generally gives you a negative value. So your enthalpy change is going to be exothermic, right? Then after that, the successive ionization energies, they are endothermic, okay? So the first electron affinity, I said ionization, I'm sorry, electron affinity. So first electron affinity is always going to be negative. The second electron, third electron, fourth electron affinity, they're always going to be positive. So that is basically with the definitions that we need to go over. So if this is all clear, we need to go ahead and discuss something known as the Born-Haber cycle. Just give me 1 second. Let me just open up the whiteboard. Just give me 1 second. All right. So the Born-Haber cycle is actually a multi-step experiment that you and I are doing. Okay. Now, the thing is that we have? Let's say we are starting with okay. Let's take period number 2, lithium and fluorine. Fine. Very small ions, lithium and fluorine. You need to make lithium fluoride. You need to actually calculate the lattice energy of lithium fluoride. Now, what was lattice energy when we were making an ionic compound using gaseous ions? So let's start. I'm starting with lithium in standard state. So the standard state of lithium is actually going to be the standard state of lithium is actually solid. And the standard state of fluorine is going to be gaseous. So this is my baseline. This is what I'm starting with. I have to take this and I have to do multiple steps and I have to make this into lithium fluoride. But I have to use my definition, which means I need to turn them into gaseous ions. But before I can turn them into gaseous ions, I will have to go ahead and first turn them into gaseous atoms. Now, we don't have to worry about fluoride, right? F2, I don't have to, I'm just for the sake of balancing, we'll have to half it. So we don't have to worry about our fluorine gas because it's already in a gaseous form. But lithium is in the form of a solid. I need to turn this solid into a gaseous atom before I can proceed with my experiment. So experiment number 1 is to take this gaseous lithium and solid lithium and turn it into lithium in the form of a gas. So I will go ahead. That will be my first experiment. And what enthalpy change am I going to be looking at? So the enthalpy change I'm going to be looking at is going to be enthalpy change of atomization, right? So this is enthalpy change of atomization, standard enthalpy change of atomization, where I am taking my lithium and I'm turning it into a gas. Now, I've taken my lithium, I've turned it into a gas. What should be our next step? Ions. We have gaseous atoms, but we need to turn them into ions. So the I will have to do two things. I have to turn my lithium into a positive ion, and I have to turn my fluoride into a negative ion, right? So to turn my lithium into a positive ion, I will have to remove an electron. And that process is known as standard enthalpy change of ionization. So I will perform ionization where I'm going to go ahead and take my um, take my lithium and I will turn it into a lithium ion. You will see I'm drawing my arrows going upwards. That is because these are all endothermic processes. This is, I'm drawing basically right now. Think of it like an energy level diagram. This is energy. So when they were at, both of them were in their standard state, it was a lower energy level. For me to take the solid and turn it into gas, I need to input energy to break the bonds, right? So it's going to be at a higher energy level. That's why it's going, the arrow is going upwards because I'm going from low energy to high energy. It's an endothermic reaction. Similarly, to do ionization, again, it's a again it's a endothermic reaction, right? Because we need energy to remove electrons, right? We've got nuclear force of attraction, all those things that you studied in AS level. So we have to remove the electron. I need to give energy to remove the electron. So it's again an endothermic process. After that, I need to take this lithium of mine and I need to go ahead and I need to go ahead and now turn my fluoride into a gaseous state, right? That's what I have to go ahead and do. I have to take my fluoride and turn it into a gaseous state. Now, before I can turn this fluoride into a gas, sorry, it's already in a gaseous state. I have to turn it to gaseous ion. Before I can turn this fluoride into gaseous ion, we have a problem. What's the problem? I have a fluoride molecule. To perform electron affinity, the definition I told you was when 1 mole of an electron is added to an 1 mole of gaseous atom. So we have to add the electron to an atom, but this is F2. Fluorine exists as a diatomic molecule. We have to go ahead and we have to first turn it into an atom. So again, I will have to go ahead and turn this into an atom. So I'm going to have to do atomization again. So I will end up with fluorine. Oh, that is going a bit too high up. Okay. I will end up getting my fluorine in a gaseous atomization. So again, I'm going to have to deal with atomization. Again, I'm going to have to input energy, turn those fluorine molecules into fluorine atoms. After I have made my fluorine molecules into fluorine atoms by performing atomization, I can now take that fluorine atom and turn it into a fluorine ion. How do I do that? By adding an electron. Adding of an electron is an exothermic process, the first one anyways. If it was second, fluorine only has a charge of -1. So we only have to worry about the first electron affinity. So the energy level is going to decrease. My lithium ion is already present in gaseous state. My fluoride ion, I will add an electron to it. You can even write down that I'm adding an electron. This is going to be enthalpy change of first electron affinity. And my fluorine will also end up getting into a gaseous negative state. Once my fluorine atom is in a gaseous negative state, the rest of the process is easy. Both of them will react together to give me lithium fluoride, and the heat energy released in the process is going to be my lattice energy. Now, there is one more arrow left to be made, and that is this arrow, where I have lithium in solid and I have fluoride as a gas, and it's reacting together to give me lithium fluoride. What should I write down on this arrow? What is this kind of an enthalpy change? This is where I said you need to remember a little bit about your AS level as well. This is enthalpy change of formation. Because you're making 1 mole of a substance from its elements in their standard state. I'm taking the element lithium fluoride in their standard state and I'm making 1 mole of a substance. This is enthalpy change of formation. So these values will be, I can calculate in the lab. I can calculate enthalpy change of formation, atomization, ionization, electron affinity, and I can then go ahead and find out the lattice energy, right? Enthalpy change of formation is also going to be a energy releasing process. So this is all going to be negative. All of these are going to be negative. These are all going to be positive because they're endothermic process. So we can go ahead and solve the question, right? Now let's go ahead and take a look at actually how we can go ahead and solve the question. Let's take a look at another Born-Haber cycle. This is making sense, right? This is all clear?
Yes.
Okay. Now let's make another Born-Haber cycle. Okay, you can make these cycles yourself. The steps are pretty much the same. Let's do something simple again. Let's do magnesium chloride. Okay. I am starting with magnesium in the standard state, that is solid. And I'm starting with chlorine in gaseous state. Oh, I don't have to have Cl2 because the balancing is MgCl2. The formula is MgCl2. So we do need 2 chlorine. Okay. Now, step number 1. Take the solid magnesium and turn it into a gaseous atom. So step number 1, take my solid magnesium and turn it into a gaseous atom. So that is going to be enthalpy change of atomization. Now, after that, I take my magnesium that is in, I take this magnesium that is now in the gaseous form and I turn it into a magnesium ion. So what is this? Enthalpy change of ionization. After that, I now need to go ahead and do another enthalpy change of ionization. Second enthalpy change of ionization. This is the first enthalpy change. Why? Because magnesium has to get to a charge of +2. Since it has to get to a charge of +2, so I will have to go ahead and do the process again. I will have to do it again. So I will again get enthalpy change of atomization, second atomization. Sorry, I'm saying atomization, ionization. Second ionization energy. Right? After I've made it into a Mg2 plus ion, I now need to go ahead and turn my chlorine gas into chlorine atom. So I will go ahead and do that. That's the next step. I take my magnesium 2 plus in gaseous state and I turn it into 2 chlorine atoms in gaseous state, right? This is standard enthalpy change of atomization of chlorine. Now, after, and I will write down a 2 next to it, right? Whenever I'm doing my calculations, I will multiply the answer by 2. Why? Because the standard enthalpy change of atomization was defined as when 1 mole of gaseous atom is formed from its elements. So right now we're getting 2 moles of gaseous atom, 2 chlorine atoms, right? So we have to multiply the answer by 2. Now, after that, I now need to go ahead and take my magnesium that is now a charge of 2 plus, and now I have my chlorine in the form of a gaseous atom. I need to take this chlorine in the form of a gaseous atom and I need to go ahead and turn it into a negative ion. So to do that, again, I will have to do electron affinity. So magnesium 2 plus 2 Cl minus in the form of a gas, and this is going to be first electron affinity, so it's going to be an exothermic process. So this is going to be delta H, standard condition, electron affinity, and it is going to be the first one. And we again have to multiply it by 2. Why? Because there are 2 chloride ions being formed, right? So the definition that we had studied was it is when 1 mole of electron is added to 1 mole of atom to make 1 mole of ion. So we're making 2 moles of ions. So we have to multiply whatever value we get by 2. Now the process is pretty much done. Magnesium and chlorine will react together to make magnesium chloride. And the final thing is to add, this is the enthalpy change of your lattice. And this is the enthalpy change of formation. So pretty much the same steps, right? The only steps that you will be adding are maybe more ionization or more electron affinity. If you had to give a charge of -2, then we would do second electron affinity as well, right? And then we would go ahead and go over some calculations. So let's quickly go over some calculations. How can we solve this? So let's say that we are turning our we are going to go ahead and take into look. Let me see if I can find values for this. Okay. The enthalpy change of atomization of magnesium, let's say that this is around plus 148. The magnesium, then we're turning the magnesium into first and second ionization energy. So 736, and we're going to do plus 1450. Then we are going to go ahead and atomize our chlorine. So energy for atomization of chlorine is around 244, and we have to remember that we have to multiply it by, okay, it's actually 122, and if I multiply it by 2, I get 244. Okay, so 122 multiplied by 2, and it gives us 244, right? Similarly, let me just pull out the data for this. At electron affinity for chlorine is going to be -348. So we multiply by 2. So we get -696. Lattice energy we have to calculate, and the value for formation is -641. So how are we going to go ahead and now do these calculations? So this is what we're going to have to find out. The enthalpy change for the lattice, right? So the enthalpy change of formation. So we are going to be subtracting the arrows that are going in opposite directions. Okay. So enthalpy change of, this is pointing downwards. Okay. So enthalpy change of formation minus, what are the arrows going upwards? The first arrow that is going upwards is atomization of magnesium 148, and then your second one 736. So plus 148 plus 736, right? Then we are going to go ahead. Just give me 1 second. Just doing the calculations, 1 minute. Okay, the other arrows that are going upwards are, we are going to take plus 1450, that is the second ionization energy of magnesium. The second arrow that is going upwards is this one, that is 244. So 244 plus 244, and then we are going to go ahead. Okay, so the cycle works like this. Okay, it's related to the concept of Hess cycle, right? So in the Hess cycle, we would subtract the two roots to get the energy for the reaction, right? The enthalpy change for the reaction. So we're doing the same thing. This is enthalpy change of formation, and from this enthalpy change of formation, when we subtract all of these values, we will get the enthalpy change of lattice. So this entire thing, all of this. So it will include the cycle, because you can see all of these arrows are pointing in the same direction, right? Since all of these arrows are pointing in the same direction, so I'm going to add all of these up, right? So I'm going to write down plus -696. And then I'm going to subtract it from enthalpy change of formation, and that will give me my enthalpy change of atomization. So I will end up getting my answer is -2523 kilojoules per Making sense? Is this all clear? Yeah, go on.
Yeah, do we have any value for enthalpy change for lattice energy?
Like I said, so this the answer that you and I just calculated, this is the lattice energy. Lattice
Okay,
energy is
okay.
something you will have, yeah, you will have to make the diagram and you will have to calculate it. They will provide you with the rest of the values, or they will provide you with the lattice energy and they might ask you to find some other one. But generally speaking, um, generally speaking, the lattice energy is something that we have to calculate. And since we cannot directly calculate this lattice energy, we have to do all of these steps. We have to do all of these experiments. If you were doing this in the lab, you could not directly take magnesium and chlorine and react them and get the net value for the lattice energy. To do so, you would have to do all of these steps. So all of these steps are known as the Born-Haber cycle. And the entire reasoning behind that is to find the lattice energy. So the answer we just got is the actual lattice energy for the process. Making sense?
Yes, got it.
Clear? Okay.
Yes.
Okay. So that is actually, to be very honest, one of the major things in this particular topic. One of the major questions that you get in this particular topic is related to the Born-Haber cycle, making the Born-Haber cycle, identifying, doing the labeling, and doing the calculations. So this is one of the major things that you have to go ahead and go over. Now, after this, what is the next step that is actually important? Let's go over that. So the next step, or not exactly the next step, but a few next thing that you need to know about is that we have to talk about the factors that affect the value of lattice energy. What are the factors that are affecting value of lattice energy, right? The factors that are affecting the value of lattice energy. So first thing is the size, ion size. The size of the ion is super duper important. How is the size of the ion important? So for the rules are different for the negative ion and for the positive ion. For the negative ion, the lattice energy gets less exothermic as the size of the cation increases. What do I mean by that? Let's go down group one. Fine.
Okay.
When I'm going down group one, I am going from, hold on, what's happening? Okay. I'm going from lithium to magnesium. No, not magnesium, sodium. Sodium, and then I'm going to potassium. So I'm going sodium plus, lithium plus, potassium plus, and below potassium we have rubidium. As far as I remember, yeah, and then it was cesium, right? So I'm going down group number one. Now, let's say that my ion is fluoride ion. So the lattice energy is going to be the highest for lithium fluoride. Okay. In fact, hold on, let me draw it in the form of a graph. That would actually make more sense. Okay. So let's make it like a graph. 1 second. Okay. I'm writing down the lattice energy over here. Okay. So, and this is, let's say this is around minus 600, minus 700, minus 800, minus 900, minus 1000. Let's say it's like that. Now, I have my ions that are positive. So I have lithium, I have sodium, I have potassium, I have cesium, and then I will have rubidium. This is enough to understand. Okay. And on this x-axis, I'm going to go ahead and draw my negative ion. So my negative ion, let's say I'm starting with fluorine. So my ion is fluorine. So what's going to happen? that when this fluorine is going to have a bond with sodium ion, the ionization energy is going to be more negative, right? Then, as the size of the cation increases, as the size of positive ion increases, it goes from sodium to potassium. Size is becoming bigger because the number of shells start to increase, right? We're going down the group. So again, the lattice energy will become less exothermic, meaning that less energy is going to be released. Then I go down to sorry, this was lithium. Okay, fine, forget it, doesn't matter. Then we go down to rubidium. So again, even less ionization energy is going to be it's going to be even more negative. Why is it going to be even more negative? The reason it's going to be even more negative is because we are dealing with a bigger size of the cation. We get to cesium again. If cesium is bonding with fluoride, it's going to have a even weaker bond, right? So the lattice energy is going to be less exothermic. Less energy is going to be released when the ions will come together. The reason for this is quite clear. The size of the cation is getting bigger. As the size of the cation is getting bigger, the number of shells are increasing. So there is greater distance between the nucleus of the opposite charged ions. So the ionic bond gets weaker. The bond gets longer, and longer the bond, the weaker it is, right? So that's how the positive ion is going to affect the um, affect your results. Now, let's take a look at the negative ion. What is the effect of the negative ion? So the lattice energy gets less exothermic as the size of the anion increases, meaning that I'm going from fluoride to chloride, chloride. From chloride, I'm going to bromide. And from my bromide, I'm going to iodide. And then I can go down further as well. I can go up to acetine, but I'm not doing that. So fluoride, bromide, iodide. So the size of the anion is increasing. As the size of the anion is going to increase, our lattice energy is also going to decrease, right? So it's going to become less exothermic. So, for example, this is what we will observe for lithium. Something like this. Maybe not in a linear manner, but maybe in a different diagonal manner, right? Maybe we will see a graph something like this. Doesn't matter. The point is that as the size of the cation or the size of the anion is going to increase, the cation is remaining the same. The cation is the same, lithium, but the size of the anion is increasing. So the ionization is going to keep on becoming less and less and less exothermic. The reasoning is the same, that as the ion size increases, the ionic bond gets longer and longer and longer. So it gets weaker and weaker and weaker. As a result, less energy is released when the ions come together. So that is how size of the ions are going to be related to the lattice energy, right? And when you go ahead and talk about it, so how are you going to explain this? If they ask in the exam, how are you going to be explaining this? So ions with the same ionic charge, because all of this, they have the same ionic charge, right? Lithium, sodium, potassium, they all have a charge of +1. Have a lower charge density if their radius is larger, meaning that sodium is also +1 and potassium is also +1. So why are we observing a difference? That is because potassium is bigger. So that same charge of +1 is now distributed over a greater radius. Since the same charge of +1 is now distributed over a greater radius, so the charge density has decreased. So since the charge density is lesser, there is going to be weaker electrostatic forces of attraction in the ionic lattice. As a result, the lattice energy becomes less exothermic. So when you're going to be explaining it, that's how you're going to be stating it. That in ions that have the same charge, the charge density will decrease as the radius is going to increase. As a result, there will be weak electrostatic forces of attraction between the positive ion and the negative ion. Hence, less energy is released, or the lattice energy becomes less exothermic as the size of the cation increases or as the size of the anion increases. So that is the first factor that we had to talk about. The second factor we have to talk about is the charge on anions. That is something we have already sort of discussed as well before. The size of ions. Charge of ions. How is the charge of ions actually affecting it? The lattice energy becomes more exothermic as the charge increases. This is quite easy to understand. The greater the charge on both the positive ion as well as the negative ion, the greater the electrostatic force of attraction between the opposite ions, and hence more energy is going to be released. It's going to be of a more exothermic process, right? And when we go ahead and talk about it, this is again due to the charge that is present. So, for example, I have lithium fluoride and I have magnesium fluoride. So, magnesium fluoride is going to be a stronger compound because magnesium has a charge of 2 plus, right? So, it's going to be able to attract each other much stronger. So, these are the factors that are two major factors that have an effect on ion energy. Any confusion in this? Anything you want to ask?
No, I
Okay.
got it.
Now, one more thing we have to discuss in this topic is something known as ion polarization. What is ion polarization? Let's understand this. So, in IGCSE, we had a very clear cut idea. There is ionic bond, there's covalent bond, and that's it. Then, when we got to our AS level, we learned that we can have something in the middle. For example, aluminum oxide can give you an ionic compound, but it can also give you a covalent compound. And as you move across the period, the ionic bond becomes more covalent in nature. Now, how does that make sense? I mean, how can an ionic bond become more covalent in nature, right? For an ionic bond, so what happens is this. Look, I have a positive ion and I have a negative ion. Both of them have an electron cloud around each other, right? The electrons, to be very honest, if we discuss between you and me, they are the orbitals, the shells are something that you and I draw, right? To make it tangible, to make it something easy to understand. But of course, an atom does not actually have those shells, those lines in real life. They have electrons that are following a certain path. Just like in our solar system, when you look at a diagram, you see those orbits. But those paths are not actually, drawn in that manner in the actual solar system. It's just the planets are actually following that path. So the concept is somewhat similar. So the electrons actually look like a cloud all around the atoms, and all of them are different energy levels. So we say that they're in different shells. Now, because they are at different energy levels, they are at different shells. So we call this electron density. We use the term electron density. Now, what happens is that let's say we have an ionic bond, right? Sodium ion has given its electron to chlorine. Chlorine has got a negative charge, sodium has got a positive charge. Now, there is an electron cloud around chlorine and your sodium as well. Okay. Now, what is going to happen? This sodium has a positive charge. So, it is going to attract some of the electron cloud towards itself. That does not mean it's going to be sharing the electrons. The electrons are still not being shared. The electrons are still clearly with chlorine. They are going to be with chlorine. They're not coming to sodium. It is an ionic bond. There's no sharing of electrons. But that electron cloud surrounding chlorine, it is going to feel a force of attraction towards sodium because sodium has a positive charge. So it will attract those electrons towards itself. So the electron cloud around chloride is not going to be a spherical shape. That electron cloud is going to be attracted towards the sodium ion. So it's going to distort the shape of the chloride ion. This is known as polarization. This distortion is known as polarization, right? So the distortion of the electron cloud around the negative ion due to the positive ion is polarization. The ability of a cation, how am I going to define it? I'm going to define it like so. The ability of a cation to attract electrons and distort the distort the anion is polarization, or another term we can use for it is polarizing power. The ability of a cation, the power of a cation to distort the negative ion, that is the polarizing power of the cation. And what is it doing? The process is polarization, and we can use the term polarizing power of the cation, right? So this is what polarization actually is. The ability of the cation to attract the electrons and distort the shape of the anion. Now, when we talk about polarization, it depends upon two things. It depends upon the cation and the anion. The larger the charge on the cation, the larger the charge on the cation, the more polarizing power it is going to have. The larger the charge it is, the more it is going to be able to attract the electron cloud towards itself. Hence, it is going to have a greater charge. Smaller the size of the cation, the stronger the polarizing power, because the smaller it's going to be, it's going to have a greater charge density. That charge is now distributed over a really small size. So that ability to polarize, it's going to be much, much higher. For the negative anion, what do we have to remember? For the negative anion, the rules that we have to remember are that, once again, larger the charge, the more easily it will be polarized. This is for the negative ion, right? For the anion. This was for the cation. And this is for the anion, right? So for the anion, the larger the charge on the anion, the more easily it will be attracted, the more easily it will be distorted. Hence, more it's going to be polarized, the more easily it will be polarized. Second thing that you have to remember is the size, right? Larger the size, the more easily it's going to be polarized. Because the larger it is going to be, so what's going to happen? That there's going to be weak forces of attraction between the outermost electron and the nucleus, because there's a lot of shells between them, a lot of electrons between them, a lot of shielding between the nucleus of the negative ion and the electrons. So as a result, the nuclear force is going to be lesser the bigger your negative ion is. So it's going to be easier for the positive ion to attract the electron cloud towards itself and hence polarize the anion. So for the cation, two things. The bigger the charge, that makes sense, because the bigger the charge, the more it's going to be able to attract the electron cloud. The smaller the size. The smaller the size, so the nucleus is closer to the electron cloud because it's in a smaller size, and the charge density is high. Hence, it can attract the electrons really easily. For the anion, the larger the charge, again, the more charge is going to be, the more attraction there is going to be between the oppositely charged anions and the cations. So there is going to be a greater pulling of the electron cloud. So the anion is going to get polarized. Who does the polarization? Positive ion. Who gets polarized? Negative ion, right? And the larger the size of the anion, the more easily it is basically going to get polarized, because the electrons are going to be further away from the nucleus. So it's easy to pull the electron cloud for the positive ion. This is all making sense?
Yes, it does.
Okay, so the reason you have to know this is because you have to relate it to the concept of thermal stability of your carbonates and nitrates. Remember in IGCSE, you basically studied that the thermal stability of carbonates increases down the group.
Yeah.
So now you know the reason for it. The reason for it is because as you go down the group, the cation gets bigger and bigger and bigger in size. Since the cation gets bigger and bigger and bigger in size, so there is going to be less polarization. When there is less polarization, the negative ion will be less distorted. And since the ion is less distorted, so the bond becomes more and more and more stable. So we need to give more and more energy to break it. So that's the reasoning for what you had studied in that year. This is the reasoning behind it, because
Okay.
of the polarization effect. So the as we are going to go down, so for example, the same is true for nitrates, if you remember, right? As we were going down, it was becoming more, we needed more energy. It was becoming more thermally stable. This is why. So for magnesium carbonate, for example, I would magnesium, since it's a smaller size, it will do more polarization of the carbonate ion. So the shape is more distorted. So the bond is weaker. With calcium carbonate, now calcium ion is bigger. Hence, the polarization effect is lesser. The carbonate ion will be less distorted. The bond is going to be stronger. So I need to give more energy. So that's why your group 2 carbonates and nitrates get more stable as we go down. This is all making sense. Any confusion regarding any of this?
No, I got everything.
All right. Okay, Anusha, I think we'll go ahead and stop it over here for today. And we can then, I think, inshallah, go ahead and then take a look at some other time. Any confusion, anything you want to ask to me regarding the topic?
No, I got it very nice. You explained it very nicely.
Thank you. Thank you. Okay, Anusha, thank you so much.